Hey everyone, in this video we're going to be looking at the logarithmic functions. In essence, they are the inverse to exponential functions. So to begin, I would like to ask you, what power would I have to raise 5 to for it to equal 17.65? I would be really impressed if you knew what it was. So let's try this one out. Maybe it's something a little simpler. What power do I have to raise 10 to for it to equal 84.2? Still can't quite figure it out how to do this, or what the answer would be. Well, okay, let's try this one. You have to know this one. 3 raised to what power equals 34.1? So you could probably argue, like we know 5 squared is 25, so it has to be something under 2. 10 squared is 100, so we know this has to be under 2. And 36, so there's different ways of doing this, but do we know a way of finding these exponents? And right now we might not. And in this video we're going to investigate how can we find those exponents. So let's review real quick. We just came from exponential functions. And what we saw with exponential functions is we have a base, which is a number, raised to some exponent, which is a variable, and it equals some number. Okay? Well, when we transition to its inverse, which is logarithmic, we have this little notation log, which is just shorthand for log. So remember, exponential functions were base raised to an exponent and we equal a number. Well, with logarithmic functions, we have a log and we say there's a base number right here, log base of some number will equal the exponent. So let's compare the two. So I raise the base to some exponent and I get a numerical value. Well, if I take the log of a certain base of the number I desire, I find the exponent that's needed. So this relates us back to our beginning. So if I take the log of, say, a log of base 5 of 17.65, what I get as a result is the exponent that would yield this number. So base, exponent, number. So it kind of works in reverse to exponential functions, and that should make sense since the two are inverses of each other. So imagine for a minute. Imagine we can look at a similar problem. I want to take 10 and I want to raise it to some power and get 176 from this. Okay? So we have base, exponent, number. Translating it over to logarithmic functions, out of log of a base 10 of my number that I desire, 176, and what I get as a result is the exponent that would yield this number. And using calculations, I'll explain further on how I'm getting this number, but we get 2.2455, which, taking it back over to our original situation, it says that if I desire to raise 10 to some power to get 176, I must raise 10 to the power of 2.2455, and I will get a number very close, again because I rounded here, I will get a number very close to 176. So logarithmic functions solve an issue where I have a desired value I want. What power provides that desired value? So let's try a couple of these out. So we're going to evaluate logarithms. Don't you guys love my nice new pen? It's purple and it's, I love it. It's right, so smooth. And in the world of pens, this is top notch, I'm telling you. And no, I'm not getting paid to advertise this pen, okay? This is just a nice pen. So let's say we have this logarithm. Log base 4 of 64 equals 3. So let's talk about this. So if I take log base 4 of 64, it equals 3. So why does this make sense? Well, if I raise 4 to the power of 3, what this whole thing says is I will get 64. Okay? Or if I desired to get 64, I must raise 4 to the power of 3. That's another way of thinking of it. So let's look at another. Let's say we have log base 3 raised to the power, log base 3 of cube root of 9. That looks a little nasty. What we find is it actually equals 2/3. Because if I raise 3, our base, to 2/3, we've seen how the denominator appears as a radical, and we have 3 squared, which 3 squared is 9. So base, exponent, number. Let's try another. So say we have log base 6 of 1/36. Okay. So you might be looking at this and you probably reason, I want to raise 6 to some power to get 1/36. Well, if it was just 36, I would say the answer is 2. Well, we find that it's -2 because, and we've seen this briefly before in this course, but definitely in other courses, that if I raise any number to a negative power, it pushes the base to the denominator. So it'd be 1/6 squared, which is where we get the 36. So let's say we have log base 7 of 1. So I'm going to raise 7 to some power and get 1 from it. I think the only possible way of doing that is raising it to the power of 0. Because 7, any number raised to the 0 power, is 1. This is actually going to be a very important situation when we're taking log of any base of 1. We find that it's always 0. That's going to be nice to know. And lastly, let's say we have log base 2 of 2. So imagine, what do I have to raise 2 to get 2? That's a lot of 2's. So what power must I raise this base to equal this value? And you think, well, I'm getting the same number, that would be just 1. Because any base raised to the first power is that base itself. Okay? So the whole idea of understanding base, exponent, and number. So let's take these examples and translate them into a more general properties that we're going to be revolved around or looking at further in this video and others. So these are just basic properties of logarithms. Okay, so the first property is one that we saw. So if I have log of some base b of 1, we saw that it equaled, and it will always equal 0. Because if I raise my base to the 0 power, that is what will make it equal to 1. In the previous examples, this would have been example D in the video, in the previous page. So let's say we have this property, log base b of b. So I'm trying to find a number that gives us b in return. Well, that was 1, as we saw in the previous page. So because b raised to the first power is b. This would have been example E. And we have 2 more. So the next one, it's kind of more of a subtle property that we were actually using, just not realizing it. Log base b of b raised to the y power will equal y. Because b raised to the y power equals b raised to the y power. You're probably thinking, what did you just say? Typically this here is simplified. So when I say a number raised to a power, we see that it's simplified to something. Okay, so in example B and C, we saw that. So in our last property, is when I have the base b, and I raise it to the power of log base b of x, we get x in return. Because this is an exponential form, so if I take this in exponential form and rewrite it in logarithmic form, we find base, so log of our base of our number equals our exponent. And again, you're probably thinking, hold on, what? And I would kind of agree with you. That property alone looks rather confusing, but we're going to see exactly how it is used. So let's have some more examples here. So let's say we have the example 6 raised to the power log base 6 of 10. Okay, so let's understand this last property. If I have a base and I raise it to the log of the same base, it equals what is inside of the log. So it's 6 log 6. So understanding this should equal 10. Okay. So where this will actually end up being used, yeah, that sounds right, is let's say I have log base 2 of x minus 5. And we want to know that for what x value will it equal 5? Let's try to reason this out. If I raise both sides, actually, why can't we just say 2 raised to the 5th power equals x minus 5? We can actually do that. Now that I think about it, I was going to go a little more complex route that would probably confuse you more. But yeah, we can take our base to our exponent equal to our number, and 2 to the 5th power. If you don't know this, it is 32. So we find that x will end up equaling 37 from this example. Okay? So let's say we have another example. So this whole concept is just example after example after example, because that's how we're going to better understand this, is just looking at examples. Log base 3 raised to the power of 81. So what does it equal? How we're going to approach this is I'm going to try to think, how can I rewrite this so that 81 is 3 raised to some power? Okay? How can I rewrite 81 as 3 raised to some power? Well, we should know that, or we can reason that 81 is 3 to the 4th power. So, looking back at our third property, base b of b raised to a power, so we're seeing that, will equal the exponent. And yeah, 3 raised to the power of 4 equals 81. And there we go. Let's try another. Let's say we have log base 4 of 1 over 64. All right, so what does this equal? I don't know. I'm thinking already that it's going to equal a negative number because we have a fraction. Let's see, 64, that's 64, that is 4 raised to the 3rd power. Rewriting this again, that's log base 4 of 4 raised to the negative 3rd. So we find right there that this equals negative 3. Okay, so the whole goal is, can we rewrite our number in terms of having this base? So we rewrote 81 as 3 to the power of 4. We rewrote 64 as 4 to some power. Okay, and I'm going to have you, before moving on to our next topic, I'm going to have you try this set of examples, okay? So log base 10 of 1 equals, next, log base 7 of 49 equals, log base 2 of 1 over square root of 32 equals, log base 5 of cube root of 25 equals, and 5 raised to the power of log base 5 of 14. What will that equal? So before moving on in this video, I encourage you to pause to solve each of these. The solutions are found, or can be found, in the notes that I've attached. So when you solve these, compare what you have to the notes that are attached and see how you did. But we're using mainly these 4 properties. And we're seeing probably rather quickly where we would use the last property, okay? So any questions or comments, you are posting them into Google Classroom or sending me a message, whatever you prefer. I want to encourage you to still, if you have questions, be writing them down as you go along. That way you don't forget what questions you had, and you can ask them, whether you come into class or just through a message, okay? So transitioning, we're going to close here in the video with a common logarithm. A common logarithm. What I mean by that is when our base is 10, this is considered a common logarithm because when our base is 10, it's used a lot in applications and sciences and other things. It's just, we often, when our base is 10, we actually often, it's often seen as just log of some number. Okay, so you'll notice I'm not writing 10 here. There's no 10, no base written. Our base is then 10, if that's the situation, okay? So when our base is 10, we would just write log with no number to the right. Okay, so going back to the very beginning of the video, understanding what a logarithm is. If I told you we had this exponential equation 10 to the power of x, what we know now is its inverse is log base 10 of x. So they are inverses of each other, and we're going to explore that more within the next couple of lessons. So with this common logarithm, all of our basic properties still hold, okay? So the four properties that we just came from, they are still true in this case. So let's see that. So I have log, again, base 10 of 100. So I'm thinking, can I rewrite 100 in terms of base 10? We can. It's log 10 squared. So we can see that it would equal 2. Let's try another. Log of the fifth root of 10. So I'm going to rewrite this with an exponent, 10 to the power of 1/5. Well, it's log base 10, so it's the exponent, 1/5. So what about log of just 10? What would that equal? Well, it's base 10, so when I'm taking log of the same base, it's going to always equal 1. So if I had log base 17 of 17, it equals 1. Let's try another. Log of 1 over 1,000. Okay, so now I'm going to have a negative value here. It's log of 10 to the negative second power. Actually, it's wrong. I could have played that off as knowing that I made a mistake, but I'm not going to do that to you guys. So 10 to the negative third power, so we would see it equals negative 3. It's all about rewriting it in terms of your base. And then lastly, if I had 10 raised to the log 7, it would equal 7. Okay? So we use our properties that we have seen before in this video, just a couple minutes ago, to do the same process. Okay, so at the very beginning of the video, I had asked you a question like 10 to what power equals 178? I believe that's what I asked you. So 10 to what power equaled 178? So, believe it or not, we can, with common logarithms, we can use our calculator. And how we can use the calculator is that there is a log button. And I want to say this, we can only use this when our base is 10. Okay? We can only use this if our base is 10. We're going to actually examine how we can change a base 7 to a base 10 or a base 13 to a base 10 so that we can use this. But that's not in this video. That's for another video. So, this log button can be found on the left side of our video, or left side of our graphing calculator, right under x squared. So, I'm not going to use Desmos this time because a couple of you had requested not to. So we see here that log is right beside the 7. Okay? So if I want to take the log, so understanding here, our base, so log base 10 of 178, and we will get from it the exponent that yields this number. So log, since it's already base 10, of 178, and we find, as you saw earlier, 2.25. And I'm realizing, I'm not quite sure how I got my other value. Earlier I got, oh, I know what it was. Earlier is 176. So hold on. So log base 176. There we go. Yep. So that was the value I said earlier in the video. But 10 raised to the power of 2.25 gives us 178. So it just matters using log on our calculator. So closing this video, There's not much to this. I want it to be your turn. Using a graphing device, evaluate log of 98.2, log of 0.041, and log of -5. Okay? So evaluate each of these. I posted the actual solutions to these in the notes, so compare what you have there. Post any questions or comments in the video, but this logarithm function really solves the issue of what exponent do I need to get a desired value. And we're going to be working more with the properties. There are more properties involved with logarithms, but we're going to save that for the next video. But until then, question, comments in Google Classroom, and we're going to have some fun with this when you come in the next day.